You're probably a bit confused about the A, I don't know if you can see it, but you know, the APQ going to A, little a, big ARS, little b, you know, those kind of rules. So I hope, as you see in the proof, that you'll see the motivation for those rules, and you put those rules into your rule base, into your set of rules for the grammar G, and the reason why you did that will now become, I hope, become clear in the proof. Okay. So now we had two cases when the stack empties between when the state of the machine P, big P, was in state little p and state little q, and the other case was that when the stack clears only at the end, when the state's in q, little q. Right, so we will do. So we'll do the first. We'll do the case where it clears only at the end. We'll do that case first. Right? That doesn't really matter which order, but okay. So we have a substitution rule that big A PQ arrow little a big ARS little b. I'm not sure if you can see it here, but here. Now that rule we put into the rule base, into our big R of our grammar, the set of substitution rules. Right? Okay, so now let's have a look at the string x and have a look at what this symbol here, this ARS, what does it generate? Well, let's say it generates the string substring y. Okay, so this ARS, that's the symbol here in the middle. Like you've got little a, big ARS, little b. So this symbol here, we assume it generates y. Okay. Now, so that means the string or substring that goes into your PDA, it will be of the form AYB, right? And y is the string that gets generated by this. Okay. Now this derivation here, you know, going from the symbol to a string that consists only of terminals. Okay. Now, you know, that's one step. That's another step in the reading. So this goes to that. Now, why is it k steps? Why k steps? Why not k plus 1? It's a real puzzle there. So you've read your first symbol, and then you start reading your second, and I'm not quite sure why it's k steps, not k plus 1. Well, anyway, think about that. All right. Now we can use the inductive hypothesis that it is possible. Now we're assuming that this you can derive from this string y in less than k plus 1 steps. We're going to use the induction, right? And we've assumed that all these rules allow you to make a derivation in k or less steps. Okay? So this one will require less than k plus 1 steps. And that's by the induction hypothesis, right? So that means that we can assume that this generates the string y, right? In less than k plus 1 steps. Okay. Now this here is a rule in your grammar. You know, when we talked in the previous session, you know, we generated all the rules of this kind. Now, because that's a rule in the grammar, that, you know, the fact that it was a rule implies, because that's how we found out, that's how we put it in the first place, for this rule to be in the grammar, therefore this contains that and this contains that, right? Before, when we were setting up the rules for the grammar, we were checking, you know, systematically going through the PDA and looking at its transition rules here and here. And if this contained that ordered pair and both, and that transition rule contained this ordered pair, if that's the case, then put this rule in the rule set. Okay? Well, this rule is in the rule set. Therefore, we have this and we have that. Okay, so we know this gives us, so we know this is from that. Now what can we conclude from that? Well, so if we're in, this is for the machine, so if we're in state P, we can transition to state R. If we're reading an A, which we are, that's the first symbol in your X. If we're reading an A, we can ignore the stack, and we can push the symbol T onto the stack. Okay. Now remember this this modified, this special PDA. It can either push or pop, and it has to do one or the other each time. Okay. It can't do nothing, and it can't push and pop at the same time. Okay. All right. So in going from current state P, reading A on the input string, we move to state R and we push a T onto the stack. Okay. Right. And now we assume here, if we expand this out, if we keep substituting, this will eventually take us to, it'll give us a string such that with the PDA, the final state will be S, okay, and with an empty stack. All right. So the final state here is S, and here we are here. And then we read a B, well that fits, right? We read a B, and we pop, you know, we pop the stack with a T on it. Yes, it does have a T on it. Because this doesn't change the, you know, it can go from an empty stack to an empty stack, or it can, or whatever on the stack doesn't change. So here, when we started here, we from here we put a T on the stack, and this won't change it. It'll well, it means it'll end in the same contents on the stack, which is T at the top, and we're about to read B, so we're in state S from here, yes. About to read B, yes. And T's on top of the stack, good. So pop the T, and Q will be the next state. So it goes from state S to Q, and do nothing with the stack. So So you've gone, so you go from A to stay A, where are we? You go from